multiple shape coexistence in nuclei. I will speak some words on his career. Paul Garrett is an experimentalist, nuclear physics, mainly working in nuclear structure. He is a professor at the University of Guelph, Canada, and he is chair of the nuclear physics, the physics department, and he was a winner of the 2023 Vogt Medal from Triumph. So he's a very distinguished physicist, and we are very happy to have him here between us. Please, Paul, come begin your speech.
Okay. Well, thank you for the lovely introduction. So today I would like to talk about multiple shape coexistence in nuclei. And well, there we go. So the first thing we can ask is, why are studies of shape coexistence so interesting? And we first have to define, what do we mean by shape coexistence? And so these are states within the nucleus that have distinct shapes from each other and are existing in the same excitation energy region. And this varies from one region to the next. So we can talk about shape coexistence, for example, in oxygen 16, where the excitation is at many MeV versus, say, in the lead isotopes or the platinum isotopes, where these excitations come down to very low energies. And in fact, some of them can change the character of the ground state. So it really depends where we are, what excitation energy we're speaking about. But it's usually pretty obvious in the context when we get there. So the shapes that we observe in nuclei are a result of the underlying nucleon-nucleon interaction, but are emergent phenomena. So if you just looked at the bare interaction, you might never guess that nuclei would possess so many different shapes. And I find that the studies of shape coexistence are interesting because it's one of those systems where we can study the effect of correlations as a function of deformation. Or you could turn that around the other way and say that you're going to be studying deformation as a function of the correlations in the same system with the same number of protons and neutrons. So unlike other areas where we're always changing particle number, in shape coexistence, you have the same number in the nucleus. So shape coexistence now is known throughout the nuclear chart, and it's really thought to probably be more or less everywhere. So this shows a nice plot of the regions where there has been well-established shape coexistence. And there's been a lot of work recently down in the very light mass regions in nickel, in the Z equals 40 region, the Z equals 50 region, and up in lead and mercury. But what's becoming more obvious now, well, at least we think what's becoming obvious, is not only are we having regions where there's two shapes, but multiple shapes are emerging. And I'm just going to highlight a few examples of those in the nickel isotopes around the Z equals 40 region, Z equals 50, and then finish up with some nice work that's been done up in lead. There's other famous examples, of course, I don't really have time to talk about, but I think Magda will say something about the calcium isotopes tomorrow afternoon. So this is a classic picture of what drives shape coexistence, in that we have these multi-particle, multi-hole excitations And this is a plot from Chris Haida and John Wood's review article. And it's intended for heavy nuclei, but the same story more or less applies everywhere. So this is a schematic where the protons are sitting at a closed shell, and you have an open shell of neutrons, and you promote a pair of particles up into a higher orbit. And so now you have valence protons and valence neutrons, which can interact. And we know that one of the dominant interactions is a quadrupole interaction between these pairs of particles. And this again is a schematic of the energy that would be required to promote these pairs of particles. So if you just put in the single particle energy, you would expect this excitation to be at very high energies. And then one gets some pairing correlations, which lowers the energy. There's a multiple factor. And the most important one is this quadrupole correlation energy. And this gives rise to a characteristic parabolic dependence in the excitation energy as a function of neutron number. So if you hold the number of valence protons fixed, as you vary the number of neutrons, you're varying the number of these quadrupole interactions, and you get a maximum in the correlation energy at the neutron midshell. So this is a very nice schematic picture. And how do we know that this is really what goes on in reality? And I think some of the best experimental proof of this comes in the tin isotopes. So this is a spectrum taken with the 2 neutron transfer reaction populating tin 118. And as we know from these reactions, they are dominated by the pairing components such that the ground state is usually carries most of the transfer strength for the L equals 0. And in this particular spectrum, the height of this peak is multiplied by 1/10. And I'll just draw your attention, there's an excited 0+ state here at 1758 keV, which is a very tiny peak. So it's about 1% roughly of the cross-section of the ground state to ground state transition. And this is very typical if you work through what you would expect in a normal system or a superconducting system, that you expect more than 95% of this L equals 0 strength really is focused in the ground state. And then you can contrast that to proton transfer reaction. So this is populating the same final nucleus, and we see this state, this is a 0+ state, that's 1.77 MeV, so that's this particular state. And now its transfer cross-section is actually greater than that to the ground state. And so that tells you something instantly, that there's very special character to this excited 0+ state. And in fact, it's reminiscent of what you would expect for a pairing vibration. This very strong population of the state instantly tells you that there's very highly correlated proton pairs in that state. So almost 0 cross-section in the neutrons, massive cross-section in the protons. And looking at the tin isotopes, we can plot the excitation energies, and here's the states in blue are what's referred to as these intruder states based on these multi-particle, multi-hole excitations. And we do see this characteristic parabolic trend with a minimum right near the neutron midshell. And detailed spectroscopy is mapped out rotational like bands built on top of these states. So this is the example of tin 116. And the numbers here are either absolute BE2 values, or if you see 100, that's the relative BE2. So it's a very strongly enhanced in-band transition. Okay, so now I'm going to jump to the nickel isotopes. and just give you a little bit of the flavor of some recent work that's been done there. So there's these highly deformed structures in nickel 56 that were observed at high spin a number of years ago, but mapping these structures as we increase the neutron number has proven to be pretty difficult. So what we highlight in blue here are states which we think are these two-particle, two-hole proton excitations. And that comes from evidence from these two proton transfer reactions. When we go into the heavier isotopes, there's some evidence here for prolate structures, oblate structures, and this is achieved by comparing what we see experimentally to theoretical calculations. And then in the middle, there's a number of 0+ states that we really don't know properly what their character are. So in these heavier nickel isotopes, there was a lot of work that was done by the Milan group of Silvia Leone and co-workers, doing experiments at multiple facilities, bringing all this data together and really mapping out to very high excitation energies, these low spin structures, and then doing comparisons to Monte Carlo shell model calculations. And from the correspondence, then they were assigning the shapes of these. This is the classic T-plot that's often done with these Monte Carlo shell model calculations. And one sees the coexistence of spherical minima, an oblate minimum, and prolate minima. And again, from the correspondence of the calculations to the experimental data, they make this suggestion that these multiple shapes are occurring. So this isn't proof that these shapes exist, but it's highly suggestive. And one needs to do more experiments to really try to understand the shapes of these states. A critical piece of data that's often used in shape coexistence studies are the so-called rho squared of E0s. So this is the E0 operator, which is sensitive to the mean charge square radii. And if you just take a simple two-state mixing model, you can have an expression for the rho squareds that involves mixing amplitudes of the two states, so alpha squared and beta squared, and then the difference in the charge squared radii. And in order to generate these large E0 strengths, we believe that you need fairly strong mixing between the two states, and also a large change in the radius, meaning a large change in the deformation. And that picture works incredibly well, almost always. And we have a problem, though, with these nickel isotopes, because we see incredibly large monopole strengths connecting 2+ states. So in nickel 58, in nickel 60, and there's no good explanation for these. So very detailed large-scale shell model calculations were done by Alex Brown. They could not reproduce this strength and this obvious mechanism of having a shape coexisting state where you would build a rotational like band on a 0+ excitation. Well, the 0+ excitations are lying above these 2+ excitations, so it's not obvious where this strength is coming from. So if we believe this kind of simple explanation, it breaks down in these nickel isotopes, although perhaps it returns and works when we get a little bit heavier. So there's still a lot of work to do, even on one of our basic probes that we use for shape coexistence. So moving on into the higher mass region, Z equals 40 and 50, and this is where I'm going to spend the bulk of my time. We've known for a long time that shape coexistence occurs here, and there's this beautiful work that came out of the Warsaw group looking at molybdenum 98 and molybdenum 100. And what I show in this plot here, these are the so-called Q squared invariants and cos3 delta. So these are made by summing over many matrix elements that you would extract from Coulomb excitation analysis. And the only thing you really have to remember is that this Q squared is going to be proportional to the deformation squared, and cos3 delta, this is acting like cosine of 3 gamma. So if we just looked at molybdenum 98, for example, we would say that we have two 0+ states with roughly the same deformation. And it's only when you look at this other invariance that gives us the degree of triaxiality that you realize that, well, actually, no, even though they have the same magnitude of the deformation, they're actually drastically different shapes. So if you didn't have this Coulomb excitation study, and you were only looking at absolute BE2 values, you would say, well, I have the same deformation in these two states, whereas in fact they are fundamentally different. And we see when we move across the molybdenum isotopic chain that as this 0+ excitation lowers in energy, this rho squared, so this E0 transition becomes progressively stronger and stronger, which makes sense in this hand-waving argument of two-state mixing. We're lowering the energy between those intrinsic states. So one might expect that the mixing would increase. Now there was a talk yesterday afternoon by Jose Enrique that really focused a lot on these zirconium isotopes. And these zirconium isotopes and several different isotopes in this region, strontium, yttrium, niobium, and so on, they have this drastic change in their ground state structure as you go across n equals 60. And it's reflected in this isotope shift where one sees going from n equals 58 up to n equals 60, a very large change and not at all smooth in the isotope shift. This is also reflected in the 2+ excitation energy. So this is the excitation energy of the first 2+ state. And we see in zirconium and strontium isotopes this very rapid drop at n equals 60. And correspondingly, there's a massive rise in the BE2 value. So this all points to going from some configuration in the lighter isotopes, which is perhaps spherical, into a well-deformed right at n equals 60. And unlike many other regions where this occurs over a wide range of neutron number, here it really happens between 58 and 60, which then leads to lots of discussions about quantum phase transitions occurring. So in these zirconium isotopes, the traditional way of looking at them has been to assume a shape coexistence and between a spherical and a deformed configuration. In the Monte Carlo shell model calculations that were published now about 8 years ago, they actually predicted multiple shapes to occur. And this is just some plots out of their paper showing how, for example, the proton occupancy numbers can change drastically from one 0+ state to the next. And this was an example of a so-called type 2 shell evolution, where because of the tensor interaction, when you promote particles, or you put particles in the neutron shell, this lowers the energy of the proton G9-halves, which then increases the number of particle hole pairs you can have, and you get into this self-reinforcing mechanism, so that the single particle energies actually evolve from one state to another. So this is all based on theoretical calculations, and now the question is, does this actually occur? So motivated in part by this, but also just the general interest, there's been a lot of work that's been done recently on the zirconium isotopes approaching n equals 60. And I want to point out in particular, in zirconium-98, there's been two recent works that were done. One that involved measuring lifetimes following fission. And this is the result in this lower panel, where they were suggesting that these excitations be put into a series of deformed-like bands. And then another work that came out of Cologne involving lifetime measurements following a transfer reaction, they had a different interpretation. So there were vast differences in the lifetimes measured between these two works, and also a big difference in how they were interpreted. So that's summarized here with these are the same states on the left-hand and right-hand side, but the results of two different measurements. So all these numbers on the transitions are the BE2 values. And there's critical states where there's vast differences in those BE2 values. And there's also this large difference in how they are interpreted. So in the work of Singh, they interpreted this sequence as a deformed band structure. And the work by Karyonchev doing an IBM calculation with configuration mixing, these were interpreted more like quasi-phonon states. And an absolute key between these two is this transition between a 2 and a 0. So in the Monte Carlo shell model, this was predicted to be 49 Weisskopf units. And in this configuration mixing picture, depending on how you did the details of the mixing, but it was somewhere on the order of several Weisskopf units. Now, the previous branching ratio for this particular transition would give you something like 500 Weisskopf units, which everyone recognized was pretty ridiculous, and something had to be wrong. So that data was essentially never taken into account because of this problem. So we did measurements on this particular isotope at Triumph some years ago with our 8-pi spectrometer. And one of the issues that maybe contributed to this branching ratio problem is, in fact, that this 155 kilovolt transition connecting this key 2 to 0 appears as a doublet. Now, we could, with our data, we had lots of statistics, so we could take a coincidence gate on this particular transition, which then really isolates this. And we saw this, we did see this transition in our coincidence spectrum, so there it is. It's small, but it's definitely there. And we remeasured the branching ratio, and previously it was about a 1.5% branch. We find it to be about a 0.1% branch, so it's a factor of 15 reduction, giving us a BE2 value of about 40 Weisskopf units. So this is the picture now that we've put together with all of our new branching ratios, and we do favor this band structure interpretation, which seems to match reasonably well with the Monte Carlo shell model. But don't get too excited, because the other 0+ structure now does not match at all with this Monte Carlo shell model prediction. So what we're seeing here is it looks like we have these spherical-like configurations characterized by rather weak BE2 values, a configuration with some moderate deformation, and then a much more highly deformed. We were able to also map out additional 0+ states, 2+ states from our angular correlations, and we started looking for the excitation built on this next 0+ state, and we couldn't find any transitions from these 2+ states that favored its decay to this 0. So we really couldn't find that band member. And the only state that did seem to preferentially decay here was up at 3.2 MeV. So maybe this is another spherical configuration. We have to do some more work on this, do another experiment to get higher statistics to really rule out any of these, but that's what it seems to be. So from that same data set, we also had data on strontium-98. So this is sitting right at n=60, so we expect these deformed structures, and the ground state band is definitely deformed. There's the well-known excited 0+ band starting at 200 kilovolt, and we've been able to establish a new 0+ band. So these states were known before, but the spins weren't well determined. And we've been able to pin down these spins, and perhaps we have the band head of a K=2 band. Not sure about that yet, because we haven't found the other higher band members. But when we do a comparison between what we see in zirconium-100, so that's at n=60, and strontium-98, which is at n=60, there's a remarkable similarity in these structures. And the strontium-98 case, from a detailed Coulomb excitation study, we know that this band is prolate deformed, and that comes from the spectroscopic quadrupole moment of this 2+ state, and the quadrupole moment of the 2+ of this band is consistent with 0. So that's kind of like a spherical-like configuration, so very weakly deformed. So we can bring all the information together that we have on strontium, zirconium, molybdenum, up into the ruthenium, and I'm plotting here these Q² invariant values. So remember, this is proportional to beta squared, and then labeling them by the shapes, the favored shapes, that either comes from this cosine 3 delta or from the spectroscopic quadrupole moment. So in ruthenium, we really have prolate-like ground states, but the excited states in molybdenum, or sorry, ruthenium-104 is known to be triaxial. That was from Coulomb excitation. When we go to molybdenum, we have the ground state, which appears to be triaxial, and the excited state more prolate. Here's the results from the Coulomb excitation study on strontium, where the excited state in 98 is spherical, the ground state is prolate. The ground state of 96 looks spherical. And then in zirconium, there's been no real firm evidence of the shapes until there's a very detailed Coulomb excitation study done by the group from Florence, Naomi Marchini, and the shape of the excited 0+ state is now known to be oblate. So we have in this region oblate, prolate, spherical, triaxial. We can now put our new data for the third 0+ band in zirconium-98, and that's the point here. So in zirconium-98, just looking at these Q² values, it now looks like we have 3 different deformations. Okay, I'll take the last few minutes to zip through. Of course, I can't say anything. Yes, I am out of time. I can't have a talk without saying something about cadmium isotopes. So there's been a drastic change in their structure from 30 years ago, where we believe that they were spherical vibrators and even up to N=6 phonons. And we suggested a few years ago that these states were rather exhibiting multiple shape coexistence. This plot is the wave function distributions in the beta gamma plane that came out of calculations done by Tomás Rodriguez. So one sees the distinct prolate, triaxial, and oblate shapes occurring. And this was put together really by combining detailed data from beta decay and N prime gamma measuring lifetimes, so that we could build up these band-like sequences. And again, these transitions are labeled by absolute or relative BE2 values. So it really does look like band structure to us. And we suggested that indeed this was the case, that these excitations were exhibiting different shapes. Now, one has to then try to go out and prove that, but just comparing to calculations doesn't tell you for sure what the shapes are. And there's lots of evidence for these intruder-like shape coexisting configurations in the cadmium isotopes. And we decided to focus on cadmium 110. And so we've done a lot of Coulomb excitation studies using multiple beam target combinations, starting in Warsaw, going to Lignaro, and then finally to argon with Gratina, in order to try to really pin down the nature of these shapes. So this is the Coulomb excitation spectrum that we took in argon. And we believe we have sufficient data now that within a few years we can tell you for sure. So I think I'll just skip to my summary. And shape coexistence. So it was thought to be a rare phenomena, and now we believe it's pervasive. And I think there's some emerging evidence now of multiple shapes that are occurring, but we have to do a lot of work to really make these firm. And lastly, the people who were most directly involved in these decay studies that I was highlighting. Okay, thank you.
Thank you for this very nice presentation. Are there any questions or comments? Yes, Civitarese.
But the pairing, there is, contribution to that quadruple pairing on top of the quadruple history. So, and they will make a competition. If you have something two shells by the way of pairing, and then the quadruple coming from the neutron side will mix with them. So, can you please comment on this?
Yeah, that's a very good point. And if I just quickly go back to here. So to that point, if you look at these two neutron transfer amplitudes, this is the first 2+ state. So it's very strongly populated, and certainly quadruple pairing is playing a role there. Now, in these calculations that are done, yeah, that's a good question, because now I want to say that it's not taken into account.
Yeah, that's my wrong, because
yeah.
So you work in the standard QRPA or RPA formalism. Then you write down the separable interactions, and the pairing channel will come in automatically. You are adding the quadruple pairing to the normal quadruple. Yeah. And then you get the funny competition between it.
Yeah, right.
So
right. But yes, if my memory is correct, in these calculations that Thomas Rodriguez does, quadruple pairing is not taken into account. But I could be wrong on that. It's really, you're really probing my memory.
No. Yes, just a question on the nickel case, where this rho square is, you say, is proportional to the mixing coefficients, but it's also proportional to the change in the mean square radius.
Yes,
And,
yes.
and this has a role because, no, I'm just guessing that when you excite particles in the nickel case to the P3 half that has a larger radius, this may have a contribution.
Yeah, so like I say, Alex Brown tried to calculate this and just failed horribly. And these were very large scale shell model calculations. He could reproduce many of the other features, the excitation energies, the BE2 values, but when he came to the rho squareds, it just did not work.
Well, this may have a consequence in the change in the radius. Maybe it is interesting to try that result. Thank you.
Just a question about, so the work that you're doing, it implies stable beams, radioactive beams, and a series of techniques and a lot of systematic studies. Can you comment about the experimental methods? Do we have enough tools and toys and methods to do this type of work? For example, the role of conversion electrons, or even polarization, tritium beams.
Yeah, okay. So we have an advantage with these nuclei sitting at stability or near stability, in that you can bring all these different tools to bear, the transfer reactions, stable beam experiments where the strength of the beam is not the problem generally. Now, you mentioned, having conversion electrons. These are notoriously difficult experiments to do. The vast majority of the knowledge on E0 transitions are really between 0 to 0 states. And if you want to extract the J to J E0 component, you have to measure your conversion coefficients, and these are usually on very large backgrounds, and then subtract off the M1E2 contribution to that electron intensity, and that's why we often end up with things with extremely large error bars. Then once you have this E0 intensity, well, you also need the lifetime to be done. And again, if you are looking at stable isotopes, you can do techniques, PP prime, NN prime, for example, to get at these low spin structures. But some of these facilities are disappearing where you can do those measurements. And yeah, and once you go into the radioactive beam side, then you're always fighting with beam intensities, which.
So what about the rho squared, the cadmium isotopes? So there are some data, I believe. And to what extent these beyond mean field calculations can reproduce them?
Now, did I put that in my backup? Let me go into the backup. And of course, I didn't put that particular one. Yeah, it's hit and miss. So we did publish the comparison of the rho squareds in 110 and 112 in a conference proceeding. And for some transitions, it's in the right ballpark. Generally, they're much too large, generally. But in these calculations that Tomas does, often it's the case he has a little bit too much deformation. And he understands the reasons for this. And it's like someone mentioned the other day that, you know, theorist talks and I understand it, and 30 seconds later, I forget the exact reason. But yeah, it's often the case that it's a little too large.
Jorge.
We understand that you want to pay a price in surface energy by deforming it because you gain an enormous energy in the Coulomb piece. But here, essentially, you don't gain anything with Coulomb because essentially you're in the same region. So where do you gain where you lose by essentially not having a spherical surface?
Where do you get? Okay. Maybe it's quicker if I do this. So the main gain is coming from these quadrupole interactions between the particles. This, you know, while it's a schematic calculation, it really shows that the dominant term, at least in heavy nuclei, is coming from this quadrupole interaction. So once you have these valence particles, this is really going to drive the deformation.
Is it very naive to believe that you might be getting some kind of insightful picture just from the liquid drop, right? Because in the liquid drop, you say, okay, so I'm going to sacrifice surface energy to gain some other place. Do I really need absolute microscopic calculation to understand why do I favor shape coexistence?
I want to say yes, but there's other smart theorists here who would be much better to answer that question. That maybe, Pete, you have
Well, that is he wants to speak. And Peter, I asked him if he can go on this discussion, and he said yes. So we give you time for this discussion.
So just a quick there's a question about the quadrupole pairing. With some Chinese colleagues, we're using generalized pair condensates where there's no restriction on the angular momentum, and still preliminary, but we actually see many more minima, shape minima, when you allow for generalized pairing. And so indeed, things beyond just J=0 pairing going quadrupole or just arbitrary doesn't seem to increase the number of minima. We're still trying to make it presentable, but just wanted to comment on that.
okay. That's very interesting. Thank you, Cal.
I think it's over. Thank you very much for the questions and for the answers. Let's thank again the speaker for this night. Well, our next speaker is Ronald Garcia Ruiz from Colombia. He's an assistant professor at MIT. His studies are mainly on laser spectroscopy techniques to study properties of atoms and molecules containing short-lived radioactive nuclei. He was the winner of 2023 Sloan Research Fellowship. In 22, he was the winner of Stuart Friedman Award in Experimental Nuclear Physics of APS. 2022, he won the Young Scientist Prize in Nuclear Physics of IUPAC. 2021, he won a National Academic Award in Colombia. In 2020, he won the DOE Early Career Researcher Award. So there are more awards, but I stop here, okay?
Thank you very much for the kind introduction.
So begin.
Yep. So yeah, thank you for the introduction and to the organizers. So I'm very excited to show you some of the work that we are doing. So this is a cartoon. So where we have neutrons, protons, and electrons that thanks to the development of radioactive beam facilities and laser techniques and a lot of AMO techniques, we kind of are able to control the number of protons, neutrons, and electrons. I want to say to our will, but as much as nature allows, and then we can create very different atoms and molecules. And they are interesting because we can create molecules like this one that they can amplify a particular nuclear or particle physics phenomena. And let me start with the big picture motivation of this work. So one of the main goals that we like to explore, and hopefully we hope to contribute, is we know there are some open questions in our understanding of the universe. So we know that there is more matter than antimatter. We know that there is dark matter. This is very well known, right? We haven't seen the violation of some symmetries like CP violation in the strong force, though it's incorporated in the standard model. We haven't seen that so far. And this naturally leaves us these questions to the possible existence of new particles. And those questions, although they might appear to be very different, so they are correlated in many scenarios, and one of them is they can be correlated to CP violation. Okay, new sources of these fundamental symmetries can provide answer to those questions. And one of the simple observables that is related to CP violation, and I'm going to speak about time reversal violation and CP violation like being the same thing here, because we think that they are equivalent. So is the electron EDM, okay? Or the nuclear EDMs, or electrostatic dipole moments in general, because if you have a dipole, a magnetic dipole and an electric dipole, you can show that they violate both parity and time reversal. And then the bottom line is, by measuring the existence of a dipole moment or a time reversal violating property, then you can go and hopefully we can provide answers to these questions. And the hope is we can provide answers to all of them. So now we want to measure a dipole moment, right? So the first thing that you do to measure a dipole is you need to apply an electric field, because experimentally, that's what we measure, right? Very simple. You want to measure an electric dipole, then if it is too small, then you want to apply the largest possible electric field. Okay, that's the principle of the technique. And why molecules is because the molecule does the job for us. Okay, the molecule provides this electric field. So that's the main idea. And how large can be the electric field? So how large can be this electric field? Sorry, having problems with my pointer. So this electric field, if you just polarize with literally a battery, so the internal electric field that the particle experiences in the molecule, in this case the electron, can be of the order of gigavolts per centimeter, okay? That's extremely large. Just to put in context, the best that we can create in a lab is of the order of kilovolts, hundreds of kilovolts per centimeter. So this works as this gigantic electric field that we can only produce in systems like some of these dipolar molecules. And indeed, this advantage of molecules is now taken to provide the best constraints to the electron EDM. And we want to do something similar, but with the nucleus. What you can see, and I can put this in this cartoon picture, is that the the molecule is going to provide these electromagnetic fields that are gigantic, and then the nucleus inside the molecule is going to interact with these external fields. And then this is very useful because we can measure properties that has not been measured yet. So this is a cartoon, and why molecules and not the atom. So in an atom, you can have typical orbital, like let's say the orbit that has the best overlap with the nucleus, that will be the S orbit. And that's great, but it has a spherical symmetry. So we're kind of blind to what happened inside the nucleus. So there is no net electric field, okay? It's zero. But it's very useful because we can learn about properties like the long-range interaction, like the electromagnetic properties of nuclei, like nuclear radius, spin, magnetic moments, and quadrupole moments. These atoms continues to be very important, and they continue to give us those very important properties of nuclear structure. Now, the new part with molecules is that I can take an atom, like radium in this case, that was initially in this spherical S orbit, and then I can put something like fluor, and this push the electronic cloud. And this is great because now the S orbit in the atom becomes a sigma orbit in the molecule. Now I have a good overlap with the nucleus, but it's deformed, okay? I can ask my electron, go inside the nucleus and tell me what's happening inside, in a way that we cannot do with atoms. Then we can be very sensitive to the short-range electron-nucleon interaction and in general, the electroweak nuclear properties that so far are pulling on. And interestingly, because it's the weak interaction, then they violate symmetries. See, in particular, parity and time reversal symmetries. And this can have many advantages. I'm just going to focus in a few of them. But yesterday we spoke, okay, can we measure, one of the theories asked, can we measure the neutron quadrupole moments? This can be a way to do that, right? Because when we access to the weak interaction, then we will be playing mainly with the neutrons because the weak charge of the neutron is far larger. So it can have many advantages that we haven't seen before in atoms. So let me try to quantify a bit what we are trying to find. Dry molecules can be very complicated. So this is the particular case for a diatomic molecule. So the typical energy levels, the electronic levels, are electron volts, like in atoms. But we can also have vibrations that are like 10 to the minus 2 electron volts. We can have rotations. And at some point, I'm going to have the interaction of these electromagnetic fields produced by the electrons interacting with my nucleus. That's the hyperfine structure, very similar like atoms. And here's where our work as a nuclear physicist starts, because when we can be sensitive to these nuclear properties, and if we go beyond, at some point at the 10 to the minus 12 level, we'll be sensitive to the weak interaction. The interaction between WC inside the nucleus is going to influence the electron energy levels or the Z exchange between the electron and the nucleus. And if the properties like the electron is not a point-like, or we say it has a dipole moment, or the nucleus has an electric dipole moment, or in general, time reversal violating properties, we expect they are going to contribute to this. So now that's the main idea, and the good news for us is that these terms, although they appear to be very small, they come as a product between a nuclear parameter and a molecular parameter. So the molecular level, we know that this scales very fast with the atomic number and the energy difference between states of different parity. So you always have these denominators that in atoms are electron volts apart, and in molecules they are micro electron volts apart. So you get these huge amplifications from going from the atom to the molecule. So you have more than 10 to the 3 enhancement in these kind of terms. And at the nuclear level, this scale with the atomic number, the mass number, the quadrupole, and the octuple deformation. So if you select the right nucleus, like radium, then you can amplify this term at the same time. So these terms that appear to be very small, if you select the right nucleus inside the right molecule, you can amplify by more than 10 to the 6. And that was the motivation of our work. They appear to be very small, but if we put the right nucleus in the right molecule, we can take the very best of molecular physics and nuclear physics to amplify this phenomena. And in particular, a molecule that is radium fluoride that motivated the work that we are doing. So now it's very hard to say, okay, what does it mean in the context of all our experiments? It's very hard to put that in the same plot. This is an F4 with many caveats, okay? But this is trying to measure a dipole moment is like constraining the existence of a new heavy particle, okay, that will induce a CP violating phase. We know this limit, that is the LHC limit, right? That's from the Large Hadron Collider, about TeV scale. We know that there is some CP violation in the standard model. That's this background here. So we expect to see some CP violation in between. This is what we call the windows of discovery. And EDN experiments like neutron EDN, they are already going at the scale of the LHC. So these are very exciting experiments, the Mercury experiment and our EDN experiments with atoms. Now, if we just put a few molecules for a few milliseconds, we can already be very competitive with these radioactive molecules. And having a few more molecules that is really more or less the state of the art molecules, then we can go far beyond. And with numbers that are not so crazy that people have done in atoms, then we can really fully cover these windows of discovery. And that was quite exciting for us. We have a system in which we can fully cover this window of CP violation, where we expect that, far beyond what we will ever do with a large collider. And likewise, because we are playing with the nucleus, we are exploring also CP violation in the hadronic sector. So that's the limit of what is called the theta QCD, these parameters that tell us about the degree of CP violation in the standard model. This is the current constraint, and those are what we can potentially do with these kind of molecules. So that was the main motivation to say, okay, we should do something for these kind of systems. But when we started the experiments in 2018, 2019, very little was known about radioactive molecules, not to say not much about spectroscopy, and certainly nothing about this particular radium fluoride molecule. So we have to start from the very beginning, step by step, and hopefully one day go to measure these nuclear properties. So how the experiment works, so we have to create a molecule. So we create this molecule at CERN with high energy protons, colliding in an uranium target. We produce very hot molecules. We produce a gas of almost any atom and molecule that you can imagine. So this is a very hot environment. And then we can send this molecule. We need to separate that. All of this is done at the Isolde CERN. So then we can send into a gas field trap that is located at the Isolde, where we can buffer gas cool to room temperature. And then we can send to the isol trap. They were helping us to really identify that we were producing the molecule with very high precision, the mass at least in 1 × 10⁵. And once we are sure that we can produce the molecule, we send that into the Crispin line at the Isolde, and at this point we have about 10⁵ molecules. To do all of this, we need to play with the molecular ion, but the molecule of interest is the neutral molecule. So we need to neutralize at CRISP by colliding with a sodium gas. And then when it's neutralized, we can send different lasers that we can use to measure the structure of this molecule. And the idea is if the molecule is neutral, it just follows the same path, but if it interacts with the lasers, it gets ionized and deflected, and then we can see counts in our detector. So the experiment works very simple. Like you have 2 lasers. This is always present, and you scan the first laser. If the laser doesn't interact, we don't see anything here, just the molecules follow as a neutral molecule. But when the first laser is on resonance, we ionize the molecule and detect that. And this is very simple because this directly gives us the energy levels of this molecule. So I don't want to go to more experimental details, but my PhD student did a very good job in producing a video that displays all of these particular experimental details. I hope you will enjoy that. See?
some bass and drums, cause I'm about to go crazy dumb. Pay me some attention and I'll educate your cranium. Crystals, yeah, we're laser numb, sapphire and titanium. But wait, I'm out of order. So let's start it at the target. We irradiate uranium, then some decays to radium. Inject chlorine, we're making some radium monofluoride molecules. They're pretty hot and they gotta be cool. Prior to use the spectroscopy tool, plants from good and they follow the rule. Energized with the night. Follow my 50 have a school. I don't sweat it, don't matter. My truth, I can't break down kinematic region. 40 kpm. Yeah, that's electrostatic extraction. Next we filter, then we trap a flap, quadruple attraction. We'll trap, we buffer gas them and causes cool reactions. The ions are static, scattered, not adiabatic. The cooling's automatic. Yeah, it's quite a useful tactic. You gas collisions, induce a few transitions, reducing our partition function, thus upping precision. We're on to the charge exchange, gotta change my flow, make the bar the flame for the through a sodium vapor, R8F, an electron into a molecules, exit the chamber, like the rest, like see y'all later. Now we're back to the price that place, scanning with number and logging the data, state of annihilated, level function, the molecules are resonating, this product is strong, not one from our paper in Nature. Post 55 nanometer light, we are excited. Higher lines, they spin laser resonate. I am the detected was like
We'll see a few examples of radioactive molecules having the ability to modify the neutrons and protons inside the molecules, allow us to explore very different phenomena.
All right, we've covered methods. Let's focus on results and goals. First of all, we had to probe positions of the manifolds for vibration normal modes, plus strength content factors. So we know if we could trap and slow, gamma damp, molasses cold. I'm talking laser cooling, if that wasn't understandable. It's important for precision measurement on things like anipodes and moments that don't get compared. Plus deviation from cooling the every time reverse breaking apparent polarities, find such a confidence, track regularity. The life that we produce scarcely some of these factors and have apparently from certain structural irregularity. Like the formations of large angularity. Got all that? All right. They magnify permanent dipole moments. They have more transitions to measure isotopes, like components that are higher than the lowest standard model effects. Account for them all. Then what do you were left with something like said, take a sign of 17 after effect bosonic coupling strength, excellent field, and shut up, we'll check, shut up the bulletin. And we're doing this tangle measurement because nobody knew that they put that as quantum with trapped.
Kind of flow.
Most of all, our science could have practical appliance, like nuclear optical clocks. Sticky timers. And as long as Ford of plastics, you'll be ultra narrow line would we keep climbing ever higher, standing on the backs of giants. It's certain ever been triumph. Looking for PT, we'll find it. Then our paper, we would write it. And then you should probably cite it. Oh, my bad, I got excited. I'm just saying, features bright and all the factors in alignment. That's a wrap. Hope you liked it.
Right, yeah, that was a wonderful job. And really, all the experimental details are there. You can find that in Spotify. Yeah. So the good news is we succeeded. It was very successful. So we managed to measure the energy levels of this molecule. I should emphasize that was a big effort. Many groups are dissolved working us to accomplish this goal. So we were able to measure the electronic levels, and to our surprise, we called the attention only from the physics community and also the chemistry community. It was very exciting to see that we can do useful things with the precision that we have now for other fields. So we are far away, we can already be useful. But that was 2020, this really gave us energy, and then we can start playing with to play the games that we'd like to play as a nuclear physicist, add neutrons into the molecule, right? That's what we'd like to see, isotopic changes. And that was also a nice surprise. So for those that are familiar, just by adding a few neutrons, 1 or 2 neutrons, we can have very big changes at the molecular level. Big is of the order of gigahertz. So for those that are familiar, those is big, at least unexpected for us in a molecule. So at this level, we can access already observable, like the nuclear radius. And that can be interesting for our actinide elements that so far are very hard to extract as atoms. So that was great, but we wanted to go beyond. So later on, we did several experiments where we improved the precision. That's what we did in 2020, and that's the precision that we have now of this experiment. So now we are very close to the natural line width of these transitions. And I didn't mention, but this is very important, this molecule was predicted to be very good for laser cooling, and now we identify a laser cooling scheme. And this is very unique in molecules. Laser cooling in atoms is a very well-established field, but the molecule is an emergent field. Because the molecule can have 10 to the 6 levels, so you excite, in laser cooling, what you want to laser excite the molecule or the atom, and it should come back to the same level. But in a molecule, you have 10 to the 6 possibilities. It was almost impossible to do laser cooling. But molecules like radium fluoride, like this one, you excite them, and although it has 10 to the 6 possibilities, it prefers to come back to the ground state, what is known like very diagonal Frank Condon factor. And that's very unique. And this molecule turns out to be particularly diagonal. It works effectively as a 2-level system. And that's great news for us as a precision experiment, because eventually we'd like to trap this molecule, do laser cooling, and do very precise experiments. So now that we have this precision, we wanted to go beyond, so that was great. So then we went and measured the hyperfine structure. And the hyperfine structure, that was another nice surprise. So we were very sensitive to what is known like the Bohr-Weisskopf effect. So this is an independent measurement of the nuclear magnetic moment. And this is our measurement assuming this mu dot B, assuming a point-like structure for the nucleus. And this is taking into account the distribution of the nuclear magnetization. So in a few words, we are sensitive when the electron is inside the nucleus, it sees a different magnetic moment than when it is outside. And that was a very fine effect, to our knowledge, the first time that was seen in a molecule. So that's very interesting, because that's what we would like to know, right? What's happening inside the nucleus. So that was very exciting. Hopefully this should appear in a few months. So and now it's under review. So now we are already there. So that was the long-term plan in 2020. Now we are here, 2024. And now we are already able to access nuclear phenomena, some of them that haven't been seen in molecules before, as I just showed. But we want to go beyond. We want to go to these parity violating and time reversal violating terms. So we established a new collaboration. So that's what is happening now. And now we want to start, I start with this radioactive liquid or radioactive sample to go to something like that, where I have a control molecule in a lattice that I can interact molecule by molecule. And that's the ambitions of this collaboration. So some friends at Caltech, Harvard are joining efforts. They have a lot of experience in laser cooling of molecules, stable for different purposes. And we started like that. That was last year. And this is happening very fast. So that's our testing lab for BioNex. Because it's radioactive, we have to do a lab with an unstable molecule and in parallel a lab with a radioactive molecule. So this is the stable lab. It's working. We are raising barium fluoride. This is very exciting. A cold barium fluoride, no ultra cold, but a few Kelvin. That's exciting. And we are building in parallel our radioactive lab for laser cooling of radium fluoride. So now, I told you we can amplify this electronic structure and also the nuclear parameter, but can we do more? And it turns out that we can do more. And why is that? At the molecular level, the parity violation scale with this denominator. And you can imagine that like the 2-level system, if you have 2 states of different parity, and they have well-defined parity, right? If you don't include the weak interaction, but if you include the weak interaction, there will be a mixing of these states, okay? And the mixing scale with the matrix element that connects the 2 states and with the energy difference of the 2 states. If the matrix element is small, then you bring them closer, you maximize this mixing, and that's finally what we measure in the experiment. So we measure this mixing of states of different parity. So now in some molecules, these states are so close that you can apply a large magnetic field and bring this denominator closer to 0, okay? The amplification is no longer 10 to the 3, but 10 to the 11. So I tell to the students, 10 to the 3 is great, 10 to the 6 is fantastic, 10 to the 11 really means that what we thought will be impossible can become very possible with these molecules. Now, if you ask, what kind of magnetic field do you need to do this? You need a few Teslas, which is not crazy, right? It's something that we can do in the labs. Nowadays, this kind of crossing was already demonstrated a few years ago. And it turns out that these magnetic fields, the Teslas, are actually quite good for penning traps, right? That's many penning traps work in this kind of magnetic fields. So then the idea is, why we trap a molecule in a magnetic field where the molecule amplifies this time reverse or parity violating property. And that's the idea. Trap this single molecular ion, fine-tune the magnetic field to have this dramatic amplification and interrogate the molecule. So this collaboration started a few years ago. We call this the Neptune collaboration. So it's a very cool name. And then it's already happening. So we're building the lab at MIT. So that's as the experiment looks like. It's about 3 meters long. So this is the laser system. And we have our first results just showing the progress of the technique, just showing that this is possible, right? This is not measuring electroweak properties yet, but this is showing that this is very possible. It should appear in PRL hopefully in a few weeks. And that's all. I have a problem with my pointer. I will just go closer to this. So we are not the only group working on this. There are many good people working in this field. This is a field that is growing very fast. So people are now trying to create radioactive molecules in traps or more complicated polyatomic molecules like radionuclides at Caltech, already with some spectroscopy results. They're trying to create radioactive atoms, produce ultra-cold atoms, and do an assembly to create an ultra-cold molecule. That's very exciting, happening in Chicago and Argonne, or XIV. There's a new faculty trying to use mechanical methods to slow down and cool these molecules, very complicated molecules. At MSU, JDIPSIN is trying to implant these molecules in solid and take advantage of these solids to measure the properties of these time reversal violated properties. And this is happening and this is growing. And I come to the summary of the presentation. I hope that I convince you that those molecules offer a really unique path to access the property of nuclei. You can imagine the molecule is this environment in which you put your nucleus that provide these very large electric and magnetic fields. And if you design your electron orbit, and designing means you select the right atoms, you can have electric fields, electric field gradients, gradients of the electric field, and so on and so on. So you can access multipolar moments. So there is a lot more to do, and you can access to the weak interaction, which you cannot access in atoms. That's where we are now. Hyperfine structure about this precision, but the AMO techniques have evolved very fast. I mean, this is the precision that we need to access to the CP violation close to the standard model. But I should say that in molecules, stable molecules, people already get about microhertz precisions. So it's not so crazy that we can get to that level. And let me end by saying that this is an exciting time because there are many opportunities. There are many facilities that are coming into operation. We are reaching an area of precision in the techniques, in the atomic and molecular theory, and the nuclear theory is catching up. So we're able to measure all of these fine details. So this is thanks to many people that collaborate and make this work possible. The CRIS collaboration at the Sol de CERN, and our friends from theory, they're very important to guide and motivate those experiments. And my group at MIT, that is a lot of young people that are doing all of this work they have been presenting. Yeah.
Well, that's it. Thank you for this really very interesting, beautiful. Are there any questions or comments? We still have a lot of time. Yes.
Can speak up. There is no clear structure information that there's no operations. I get the feeling that you're saying that if you just measure this, if you just measure this, now I have to speak slow.
If you measure it, then you will already come to effects beyond the standard model. But I understand that also in the other observables, there is always this correction from nuclear structure effects.
Yeah, thank you for the question. So the interesting part is because we are sensitive to we can tell the molecule, just tell us about the symmetry violating properties. So something that indeed can be confusing is, look, you are going to measure this tiny effect on the top of something very big. So that's not really the case because in molecules, we can actually sit in one particular level. And if you want to see like that, is we create a molecule, is creating a Hamiltonian. And we do a small modification of this Hamiltonian by keeping all of these terms constant. Okay, for example, applying an electric field, external field. So we know that the nuclear properties remain the same. And now we build this Hamiltonian where only these particular time reversal violating properties should have changed. And then we take the difference. So we measure directly these terms. So it's not that we are measuring a small term on the top of a very big thing. So we measure this directly. So it's directly. Now, this term is indeed the product between a nuclear and molecular parameter. And there we really need a nuclear theory to say something. Here we measure something that we expect in the standard model. And to do something with high precision, we need to know nuclear theory to some precision, at least up to some percent, right? But in the case of time reversal violating properties, because we don't expect this in the standard model, anything that you measure beyond zero is a discovery. Now, to make an interpretation, what does it mean at the standard model level? Well, that's the most fundamental meaning of that. What's the fundamental source of time reversal of CP violation? We really need a complicated theory. But for the discovery, we don't. Yeah. I hope this clarifies.
I guess you need the sort of a process where the nuclear part is completely independent. No, it's completely independent of the say the part of the current coming from the standard model. This is not the case in many processes, meaning that you measure something and the result is a product of something which is coming from nuclear structure and something else which is coming from the electronic part.
Yeah.
And it's very hard to avoid that. Think of, for instance, the double beta decay.
Yeah.
So you can estimate the limit for the half-life. And if you measure that and you get the Nobel Prize for it, nobody will know what is the value of the mass of the neutrino. Why?
Yeah, definitely. So yeah, kind of two things. So yes, yeah. So definitely you need the nuclear theory to make an interpretation that's kind of very similar to the double beta decay. So, but because we don't expect that in the standard model, in the case of time reversal violation, seeing something that is non-zero is a discovery. But yeah, definitely we encourage the nuclear theories to work in this problem and to give us the input. So now, just to be more specific about the currents that we are proving, so we are proving two things, at least, right? In the parity violating sector, so the WC exchange between the nucleons are going to generate a magnetic field inside the nucleus, what is known like the anapole moment. You can imagine it's like a toroidal current. So the interaction between the electron and the nucleus is electromagnetic. So now the electron interacts with this magnetic field that is produced inside the nucleus. But we know that this magnetic field violates parity. It comes from the WC current inside the nucleus. Now, the electron can also interact with the nucleus with Z exchange, okay? And the Z exchange can be of two kinds, axial vector or vector axial. So the vector axial is well known. That's the cesium parity violating experiment. That's the electron scattering experiments at Jefferson Lab, for example. So these ones will be sensitive to the axial vector. So that will be sensitive, yeah, to this part that is poorly known. So then the hope is that here, our role will be to guide theory. Okay, we don't know hadronic parity violation well. We don't know the coupling constants. We don't know how the interaction works. So our job here is more like guiding this development of theory. So, and in fact, we call this project Neptune because a nice history. So for those that don't know, so Neptune was the first planet that was predicted. So they did a precision experiment to measure Uranus, and they saw a deviation, and they predicted a new planet. So that's the role that we are going to play here. So we are going to measure something that is precisely predicted, and any deviation can be something beyond what we know. And Neptune was the beginning of precision astronomy. So that's the context here.
Bira, one call.
That's a bit of a crackpot question. Did I understand correctly that it is by box on magnetic quadrupole?
The magnet, in principle, yes, we are not dedicated to that, but yeah, in principle, that can be a possibility. It's not our work. So the first thing that we will be sensitive will be the magnetic quadrupole will be time reversal violating. That will be the second moment that we will be able to access. For that, we need a nuclear spin that is higher than 1/2. So we are not thinking about that. But the short answer is, in principle, yes, those kind of measurements can do it. So, I have to think. So, yeah. So I have to think because in principle, all moments should appear. So the short answer is yes, they should appear. All the moments should appear. But I need to think if they will be suppressed or not. Because this will be a nuclear spin dependent. So that's good, because that's what we want in these molecules. I will say yes, it will go there. It preserves P, or it violates both P and T. Yeah, it preserves P and violates T. So then I afraid that will be suppressed. Because our way to access is, first we ask the molecule, does this violate P? And then we can isolate the electromagnetic interaction. And then we ask, does it violate T? Yeah, so then I'm afraid that will be suppressed. Yeah.
If there are no more questions, let's thank the speaker again.
I try control it.
Our next speaker is Alfredo Galindo Uribarri from Oak Ridge National Laboratory, and he is a distinguished scientist of ORNL, and he will speak about the Neutrino program. Thank you very much.
All right. Thank you very much, Linda. I'm very glad to be here. I consider this to come back home. When I started my career, this auditorium didn't exist. I studied here at the university, so that tells you a little bit about
how long I've been on this field. How would you advance this? Okay, backwards. So a little bit about me. I study here at the National University, and I'm glad to see several familiar faces. So Maria Esther, Arturo. Then after that, I went to study at the University of Toronto, and then I worked at Chalk River Laboratories. And I actually saw Claude Bruno somewhere in the audience. That's fantastic to see many old faces that over the years we have worked in different fields. So in a way, we have gone through a series of what can be considered shape transitions, and I'm not talking just about the shape transitions we're going to have after a week here in Mexico. But then after that, I went about 27 years ago, I went to Oak Ridge. I'm also professor at the University of Tennessee. And in the last couple of years, I spent in Washington at National Science Foundation. So I'll talk a little bit about the role of neutrinos. About 12 years ago, we shut down our facility of radioactive ion beams that we had at Oak Ridge. For about 15 years, we pioneered many techniques associated with the production of radioactive ion beams. And then we saw the opportunity to go into the field of neutrino physics for a couple of good reasons, and this had to do with the SNS and with the HIFER reactor. So this shows some of the current interest we have in neutrino science and some of the synergies that exist. So we are currently involved on LEGEND for neutrino double beta decay, Prospect and coherent, Prospect at HIFER, coherent at reactor. And there are several things associated that have quite a bit of synergy with this type of work. One of them is the isotope program is handled at ORNL. And over the years, we have been interested in many ultrasensitive analytical techniques that have importance for some of the things that I'm going to be working. And of course, Oak Ridge is also known for neutron production and computing science. And some of my colleagues, they have been working on things on beta decay of neutron-rich nuclei with things like MTAS. All right, so ORNL, it really within the last 12 years has become a real hub for neutrino physics. And here is just to give you an idea of the scale of some of the experiments associated with LEGEND, Prospect, and coherent. So quickly, we have been involved on neutrinos double beta decay since 2006, already 18 years. And it has been a while over the years. NSAC, as the advisory committee for DOE and NSF, the neutrinoless double beta decay research program has come pretty much at the top. There was an exercise just recently, and still this is one of the main priorities of nuclear physics. So essentially, if this is a very rare decay is observed, where you basically have this process, we know that double beta decay exists. This will have major implications in terms of neutrinos. Just a connection with the neutrino double beta decay. For doing this type of work, this work is done underground with a lot of shielding. And one of the important things that we have to deal is with backgrounds. We're looking for signals that are going to be taken over probably the period of a decade, where we need to place about 1 ton of enriched material such as germanium-76, and then wait for this very rare decay.
that is going to have a unique signature as a small peak. This is a simulation, and many orders of magnitude we need to reduce the backgrounds in order to be able to be in position to observe it. One of the things that we had at the Holyfield facility, at the radioactive ion facility that was useful, we started the program to look for analytical techniques, the most sensitive analytical techniques, in order to look for things like actinides, like uranium, thorium, and plutonium. This is a surface ionization source. CERN uses this type of sources. Triumph uses this type of sources. And essentially, a small sample, here the main thrust is to have a very small sample of a radioactive material, which would handle the radioactive material. And we had a system of three high-powered tunable lasers that we could use to very selectively ionize and most important, very efficiently ionize actinides. So we recently have a couple of highlights from DOE MP and DOE HP. And in this talk, I want to highlight some of the role that some of the Latin American students over the years, I have brought several of them, they have played. Oops. They have played on this. So Elisa Romero from UNAM, we published in Science Reports in Nature, and this was a work that essentially we could produce plutonium-242 with an efficiency of 51%. So essentially what this is that here we go. One out of two atoms, we can very selectively ionize and detect at the end. So this efficiency is actually huge. The sensitivity is also huge, and this is a very important work that probably will have quite a bit of importance also on the topic that the previous speaker was talking. Very quickly, let me go through the neutrino. The neutrino, as we know, is a very important particle, but at the same time, there are many properties that we still don't know. This is Pauli. This is a process that is essentially a three-body process, where essentially we have on the beta decay, we have a continuum, and in order to conserve momentum, Pauli had in the 1930s to postulate the particle, and then he was concerned that maybe this particle could not be detected. This is just simply to show you the scale in roughly units of about 20 years, where major experiments, mostly associated with reactors, it has taken in this particular field, from the first observation of neutrinos to the solar neutrino problem, to the demonstration that neutrinos could oscillate, and the measurements of mixing angles. So neutrinos play a very important role in the standard model, and right now we know that oscillations exist between the neutrinos. We have three types that corresponds to the three lepton generations, and essentially, however, we know that this picture is incomplete. So we know that the fact that they oscillate implies that the neutrinos have masses, and these are some of the main important questions that we are trying to address in this particular field. Now, coming back to Oak Ridge has particular important opportunities, mostly associated with the neutron program. The neutron program, Oak Ridge has the spallation neutron source, a 1 GeV proton machine, and a linear machine followed with a ring that it can put pulse beams on target and essentially generate a series of neutrons, and there are several beam lines, mostly supporting a lot of the condensed matter work and other applications. Currently under construction, there's a second target station. It's a $1 billion project that is going to have a different time structure for, and this will be able to, and in addition to that, there will be an increase on the energy of the protons and also in the intensity. And at the same time, within the reservation, we have HIFER, which is a research reactor with a very, very compact core that operates with the highly enriched uranium. So neutrinos come from two different processes. In the case of the reactor, it's coming out through the beta decay of the actinide, the material, the uranium. So we have fission, and each of the fission fragments is neutron-rich, decays by beta decay, and it produces a neutrino. So typically, we have the order of 6 neutrinos per event or per fission. So what we are aiming to do is a very well precise measurement of the antineutrino spectra. As you see here, this is just to give you an idea of the energy scale of the electron antineutrinos coming out from the reactor. That goes up to about 8 MeV. In the case of the spallation neutron source, the process is different. This is what is called a pion decay at rest neutrino sources. And I won't go into the details, but the point here is that it produces 3 different types of neutrinos, and the energy scale extends up to about 50 MeV. Main characteristics or main difference is that here we're dealing with a huge flux in the case of the reactor. And here in the spallation neutron source, we have large fluxes, but one of the most important things is that has timing. So the sharp pulse timing allows to do background rejection that can be equivalent to several hundreds of meters of water. Okay, so some of the interactions of the neutrinos that could happen is at low energies. So we can have neutrino electron elastic scattering. We can have what is called coherent elastic neutrino nucleus scattering, where the entire nucleus is recoiling as a whole. When the condition is that the incoming neutrino has to have a wavelength that is comparable with the nucleus. And essentially the detection becomes complicated because the process will rely on the recoiling nucleus. And the other process is a process that was proposed by Bruno Pontecorvo, which is the inverse beta decay. And in this particular case, we have time correlations and spatial correlations that allow us to be able to detect the neutrinos quite well. So quick word on the coherent program. The coherent program takes place in what we call a neutrino alley. It's a service space that it happens that we have is about 20 to 30 meters from the target, and it has some overburden, about 10 meters of water equivalent from above. And it became a very good place to deploy a series of detectors in order to study this particular process. In 2017, already 7 years ago, the first observation of coherent was discovered at the spallation neutron source. And these were about 136 counts that they were taking over 16 months. And this was in cesium iodide. So this pretty much opened the door it was a process that had been predicted for more than 45 years. And it was the very first observation. Of course, it's predicted by the standard model. And the point here is that the energies, they are coherent up to about 50 MeV, but then they start losing some of the coherence. So there are some nuclear physics effects, some sensitivity to form factors, and so on, that once we enter into the stage of high precision, we might be able to see. Here is an expression for the cross-section that for coherent elastic scattering. I want just to draw your attention to this dependence of the number of neutrons squared. So the cross-sections are very high as neutrinos go, but they have this particular dependence. So this is a log scale plot. And the idea is to go and deploy some other detectors, either germanium, argon, sodium iodide. There are ideas of neon as also as a target. And this is basically to track this dependence on the cross-section of neutrinos. Now, I want you to draw this attention, these 5 points, they correspond to germanium, because germanium has 5 stable isotopes. And one idea that we are pushing is, what about if we do, instead of using natural germanium detectors, what if we have the technology for neutrino-less double beta decay to produce highly enriched germanium-76 up to above 90% enrichment? What if we were to do the same for the other isotopes? So these are the natural abundances, and in principle, the technology exists in order to do this. And together, we opened a collaboration with the group of Omar Miranda from Simvestab, and we published a paper on the novel approach for studying coherent elastic neutrino nucleus scattering. And this is basically a study of looking into the correlation, if we were to have a Gedanken experiment with those characteristics, how they would look for a SNS type of source or for a reactor. And these lines pretty much define regions where these correlations would be very sharp and well-defined. Gonzalo now is a postdoc at Valencia, and he got the Weizmann Award from the Mexican Academy of Science on his thesis. So the germanium in green, this is the typical enrichment that we have for neutrino-less double beta decay, this proportion, and a natural germanium has this other distribution. But it turns out that people have actually done germanium detectors using depleted material, and pretty much the response is very much the same. Now, this idea about using isotopically enriched nuclei could be extended to other technologies, not necessarily germanium. So, for example, there are several approaches on coherent to use things like bolometers. So any chain, for example, the thin detectors would be an interesting one, because the cross-section is not just flat or linear, but is square. So the relative cross-section between these detectors would be unique, and clearly would be clear that we're detecting, that would be a signature that we're detecting neutrinos rather than having a signal and measuring the background and then subtracting after many, many months of stable operation. All right, Oak Ridge has had a long tradition on reactor building. So over the years, 13 reactors have been built. This is the first one, the graphite reactor. And right now we are using the last one, which is HIFER. So HIFER is this research reactor. And beside HIFER, we have something that's called the REDC, where basically they have the hot cells and they can process the different actinides. So it's almost an equal facility as the reactor. And these are legacy capabilities that some of these things are hardly going to be repeated on the same way. So of course, there are many, many sources of neutrino sources, and essentially we are concentrating on what we can do on Earth. In addition to the reactor and spallation neutron source, there is also the possibility of doing a very, very strong source where we would only have one type of decay, and we're doing some studies related to that. The motivations for prospect of the reactor were two main motivations. One was that people have been doing experiments of neutrinos, and based on theory, there was a deficit of the order of about 6% on the flux when it was compared with the reactor models. And there was a speculation, the hypothesis that maybe neutrinos were disappearing into an active sterile state. So that was one of the goals, whether we could look for oscillations on a very short scale. The other motivation was, can we fully understand from the nuclear physics point of view, the neutrino spectra, can we measure it with good energy resolution? And there have been some anomalies that people have reported, such as a bump in this particular region of around 5 MeV. So there won't go into too much detail here, but there have been several complementary methods to study the nuclear physics and the beta decay isotopes. And of course, the difficulty is that in the fission process, we are basically dealing with anywhere from 800 to 1,000 beta decay branches. And from that, you can extract the antineutrino, but there is a lot of complications in the process. At the same time, this is complementary because we're looking from two different sides. We need to understand very well the process. Now, anomalies are not new in this field of the neutrinos, and in fact, it was such an anomaly that led to solving the so-called solar neutrino problem. And this was John Davis doing what I call very heroic experiments on making a measurement. Again, he started in the 70s, went all the way to 90s, and he was seeing a deficit of the neutrinos, and based on the discrepancy of the calculations, and he insisted on this, and literally this led to a major discovery. So there is this hypothesis on the possibility of adding another row on this PMNS matrix, and one can study the disappearance of the probability of disappearance of the neutrinos as a function of this function, essentially as a function of these differences in the oscillation phase, and the distance and the energy of the neutrinos. So the high flux isotope reactor, just a few words, is ideal because this is a mock-up of the real dimensions of HYPHER. So it's an extremely compact reactor, and therefore it can be considered as a point-like source for neutrinos. So we can position a detector of about 4 tons of liquid scintillator. The way that HYPHER works is that typically operates for about 28 days, and then the fuel is removed. There's a fresh core every cycle, and then that happens on roughly about 1 month. So in principle, one can get signal background measurements, and so on. Also, is a very well understood, and there's a lot of detailed core model available for simulation. Our students, they have been heavily involved on studying the backgrounds associated with the reactor. So this just tells you what happens when the reactor is on relative to the reactor is off. And you can see, because of the energies associated with the gammas, that you have a lot of capture reactions. So these are gammas that you can see even going through the pool and so on. So that's the way that it looks in reality. And essentially, data was taken on this inverse beta decay data between 2018 and 2019. This is a comparison on the size between the power reactor with a commercial reactor. So these are the backgrounds. This is a bird's view. This is a reactor pool. These are 2 beam lines that they go to SANS and other neutron beam lines. And essentially, we had a very detailed mapping of all the possible backgrounds, both in neutrons and gammas on the area. Okay. Now, we had a problem with our detector that we started losing photomultiplier tubes. The liquid scintillator that we use is a lithium-6 dope material essentially is a neutron detector. It's a basis similar to Elgin 309, where lithium is dissolved. And it became that we had incompatibility of some of the materials, and we started getting some of the photomultiplier tubes that were compromised. So we lost some of them. At the beginning, essentially at the end, we lost 62 out of 398 PMTs. And turns out that this was, what you see here is the reactor on signal in blue, the background measurement, and then basically the difference, our main measurement. And we took the approach of separating and doing the analysis of the data in 5 different periods, and that was the main role of the PhD, my PhD student from Colombia, Diego Venegas Vargas, that he looked at the data again, separated the data in 5 periods, and turned some of the photomultiplier tubes that some of the segments, this is a double readout, but there were several segments that they still had 1 photomultiplier tube operational. So that, when we turn it, that serves to veto some of the events that leak through the neighbor, and turns out that that was very, very useful. So the net result was that the signal to noise, the quality of the data improved. This is just to illustrate the 5 different periods. This is the background. So clearly we went already 1-to-1 signal to background was good, but we went to 4-to-1. So clearly the detector was well designed. And also an important aspect was that the number of events increased by about 20%. And there is something we call effective statistics that that essentially we double what we call this effective statistic parameter. So we went from a situation like this to a situation like that. Right. Now, in terms of oscillations, there has been a result from Neutrino 4 where they have made a claim about oscillations. So they have observed this on this parameter space on L over E. These are our detectors. This is coded in such a way that it implies which segment had was blind, which segment had one particular photomultiplier tube. The reactor roughly is located here, and this is the segmentation of our detectors. So our detectors are a matrix of 11 by 14 with double readout, and the difference between the timing of the two detectors gives us information about in the Z direction. So in principle, we have information like voxels of information, roughly about 15 centimeters on small cubes. So this is the way that the data was analyzed on the different baselines, 1, 2, 3, 4, 5, 6. And essentially, the bottom line is that looking in a comparison with the Neutrino 4, there is, our data shows no obvious oscillatory features in the ratio of this spectra between data and the null oscillation prediction. So this is Neutrino 4 over null, the green, and this is basically our fit where we conclude that we do not observe the neutrino oscillations. So this was loaded and appeared just yesterday and is waiting for this essentially is the last result or the main result coming out from prospect 1. So one of the main thrusts, of course, is the connection on how much we can exclude in this parameters space. And well, I might give you a little bit more details here, but the bottom line is that we have excluded quite a bit of space, including the so-called gallium anomaly, and that the Neutrino 4 best fit point is ruled out at more than 5 sigma confidence level. The new prospect data set is compatible with an absence of sterile neutrino oscillations. I already mentioned this. And what next? We're currently engaged in a joint analysis with other leading groups. Stereo operated at Grenoble. Grenoble works at about half the power of our reactor, and the diameter is about twice. But pretty much are comparable type of experiments. They have less segmentation, and Diabay, of course, has a longer distance. So essentially, we're working. The same student is working on a joint data analysis that will further push these limits, and the analysis is well advanced, and is likely that it will come in a few months. So what next? We just established a group of people interested on doing neutrino experiments of different kinds. and we're looking into now that we have very well characterized the area in front of the reactor, we're open to collaborations. We're still waiting on the development of Prospect 2, which would be a more rugged detector. It will not have the inner channels that we had in order to do the calibration, and in principle could be movable in such a way that we can do measurements with reactors that are not just highly enriched, but also that they have some mix or low energy enrichment. Now, I want to highlight the role of the students. These projects between 5, 6, 7 years is a fantastic project for a graduate student. It's commensurate with the type of, in some cases, some of them, they saw the beginning of the process, the project. They started helping on the construction of the project. They help on the data taking. They help on the data analysis. They wrote their papers. So I contend that this scale of experiments is great for the general training of students. And over the years, I had established a program with mostly people from Latin America, from Mexico, from Colombia, for summer interns. So I had brought of the order of 45 students under this program. And I think, well, one of the latest here is Diego from Colombia. Christian is now doing high energy physics. He got a APS HEP prize also for his thesis, and so on. The most recent ones, there are 3 guys very nervous with all this science, visiting the graphite reactor about a week ago. So that's the scale of Prospect. Here was assembled at Yale. Here is at Oak Ridge on the experimental place. And we had many prototypes that they were deployed here. This is a mixing tank. And these are of the order of about 100 people that from the reactor and various places. Doing an experiment like this involves a lot of people from local people. I want to finish this on a personal note. My brother was a very proud member of the university, and he passed away recently, and he published this paper. This was posthumous paper and universe on the unsettled number of the Hubble tension. And he co-authored 3 articles with the Nobel laureate George Smoot. But also he attracted some unfamous co-authors, and this is one that you might have seen recently on the news. So there is a legal process that was started, and I don't think I can go very far, but for the younger people in the audience, truth matters. Thank you.
Are there any questions, comments? Yes.
Well, thank you, Alfredo. Nice to see you. No, I'm not an expert on the neutrino part, but there are in this, we have in a point source, neutron source. Have you given a thought or are you working on these neutron oscillations? You see that with neutron oscillations, you can having high neutron flux well-defined, you can somehow produce anti-neutrons that can be detected. Yesterday, we had a session in which one of my students proposed detecting anti-neutrons through charge exchange. So if you have a comment.
Leah is talking about the topic. I'm peripherally involved on that collaboration, but Leah is doing the experiments at Oak Ridge. When is your presentation? Tomorrow morning. Yeah.
Yes, I will be talking about baryon number violation and in particular neutron oscillations tomorrow morning.
I don't see any. Thank you very much for your talk. I mean, the question is not only with sterile neutrinos, we also with heavy neutrinos, because you can really make a joint plot searching for right-handed bosons in the TeV region, and then get heavy neutrinos in the mass range say of 100 MeV as a three generation. So our expectation now is that when the accelerator in CERN is working again, they may find out some signal for the right-handed bosons, and that immediately, if it is measured, then observed, then heavy neutrinos will be there.
Right. Right.
And it's very exciting. So this plot you show with the three flavors, the U matrix and the three mass eigenstates. Now should be another matrix called that matrix V, and then will be another three mass eigenstate in the heavy side. That will be fantastic.
Thanks for the comment. I think what is important in many of these experiments, again, the time scales, we're talking 10, 15, 20 years, and many times sequentially, and many times you have an experiment and that is going to confuse the field for the next generation and so on. So the methodology and is important. The sensitivity of a well-designed experiment is important at the very least to rule out the different regions and make progress in science rather than having a collection of results that might be contradictory.
Well, exactly. I mean, because you can get a surface there where in one axis you have the right-handed current couplings, the right to left, and the neutrino mass. Then you get the surface there, and then the poor station of the standard model we are living in is just having only one of the curves. So this is the nice problem. I mean, you have the complete model. There will be a SC2 left times a SC2 right times God knows what, because the Higgs mechanism will not play for neutrinos masses.
Right, Ricardo, you wanna say something? No.
So I have a question about this neutrino 4 experiment that Prospect seems to rule out. Do we know more details about the experiment and what could be wrong?
On the
yes,
neutrino 4?
Yeah. I mean, they see a signal that you don't verify.
Like I've been in previous occasions in the search for the highest spin or hyperdeformation for two neutron emission and so on. You do your experiments, you report your experiments the best you can, but someone very senior at Berkeley told me, well, your data is going to be there, and that's what matters. That's what is important. To prove someone wrong, you really have to work
an order of magnitude with more sensitivity in order to be able to rule them out. So there are several experiments here, like a stereo diabase prospect joint analysis and so on. And we're not speculating about what might have gone wrong from them. You just simply report it based on a rigorous analysis.
I don't see. Okay, I think there are no more questions. Let's thank the speaker then.